Okay, so this year we accepted 16 papers, and we have two spotlight sessions, one in the morning, one in the afternoon, and this morning we'll have 8 presenters to present their amazing work. So let's welcome the first presenter.
Yeah, so hello everyone, I'm Gu Chol Jung from UT Austin. Today I'll be presenting BiFlex for manipulation in unstructured environment. So here we see the challenges in unstructured environment or setting. So so the robot must grasp the object with precision and when I to click the space or press the space, then it just go to the next slide. Like even though I have the
you have animation.
Yeah, animation.
Just note saying that you might not have access.
Okay.
Yeah.
So yeah, there is observed the unexpected impact for the contact reach tab. So in contact reach, the common solution are using the FT sensor, but it adds the response latency and or active variable stiffness, but it incurs a high complexity and cost. So our research is to develop a passive robot wrist that switches between high stiffness precision and low stiffness compliance without any other electronics or complex control for household object, which the weight is mostly less than 500 grams. So as technical way, it should support up to 500 grams at the fingertip of the gripper. Yeah, and the limit deflection to under the 10 millimeter. And the passively observed the forces from the high external forces. So based on our goal, the wrist must offer 2 modes. Precision mode by high stiffness and compliant mode safe interaction. To customize both critical load and the stiffness in precision mode so that wrist switches mini. So to achieve the bimodal stiffness, bimodal stiffness, we leverage the beam buckling axial load aligned with give the high stiffness, but buckling at the low stiffness. So our initial circular wrist with the straight column, the suffer yaw motion, and it has the weak rigidity. So we adopted the honeycomb lattice for the desired behavior. So we introducing the BiFlex or passive bimodal stiffness wrist through the buckling behavior. So it features 3D printed top and bottom plate for the any gripper and a universal joint for the pure buckling and TP lattice that auto switches stiffness. So this honeycomb structure vertical stiffness has the critical load are adjustable by the 2 key parameters. So as tilt angle decrease, then vertical stiffness increase, and as second, higher beam thickness increase the critical buckling load. So based on this, we customize the BiFlex for the any grippers. Based on the each gripper mechanical properties, we customize by the parameters, and they could achieve the different vertical stiffness and critical load for the 3 different grippers. So to test the compliance, we had the robotic hand wipe over the wiped over the aligned triangular peak with the BiFlex, and it clears 50 here under the 15 Newton, while the rigid wrist that limits us at the 15 millimeter, showing the BiFlex superior adaptability and safety. And for the pick and place task, to validate precision performance, we set each shelf space 10 millimeter taller than object height so that it could fit the precision mode. Next is compliance mode. The BiFlex uses the table as a guide, sliding along the surface to the grass hex branch, even with the aimed 50 millimeter low, and while keeping the forces under 15 Newton for safe and reliable pickup. So as a summary, BiFlex achieved the bimodal stiffness for safe manipulation. We demonstrate various tasks to validate the real-world performance and can be used for any other gripper by modulating key parameters. The details and website, and we have the BiFlex demo at the poster place. So thank you for listening.
Because of the because we only have limited time, so we won't have Q&A. And if you're interested, please catch the authors at their poster. And because one of our speaker has a conflict on their schedule, so we will yeah, our next speaker will be DexUMI. Okay, that's right. Let's go down a bit. Let's go smooth down. Yeah. Thank you.
Okay. Yeah, sorry about so today it's my great pleasure to talk about DexUMI. So this is our most recent work, and I collaborate with my amazing collaborator Han, and also advised by Shuan. So, all right. So, what is DexUMI? So DexUMI is a data collection system which allow human to hand as natural to transfer various robot hand skills using human hand as natural interface. So how do we achieve that? We have two key ideas. Number one is that we build an exoskeleton which human can wear and to close the action gap. And number two, we have a data processing pipeline which close the visual action gap. So let's first talk about the action gap. So in DexUMI, we build our exoskeleton such that it shares the same joints, location, and the limits as the target robot hand. And also, we share the same link length as well. So following the same procedures, we can build the exoskeleton for the remaining fingers. At this point, you can really think about our exoskeleton is exoskeleton is a version of. However, simply following the URDF often cause collision between human sim and exoskeleton sim. To resolve this, we solve an optimization problem to move the sim backward while preserving the fingertip post workspace. Okay, then let's talk about sensors. So we capture sufficient information for policy learning. We use iPhone to capture 6 DexWrist actions. And we also have wide angle camera to capture the sufficient information for policy visual observations. We also insert drawing encoder to capture hand actions. And we also install the same type of text sensor as target robot hand to record haptic feedback. Next, let's talk about the visual gap. Because of, we're actually using exoskeleton to collect data. Now we have a new problem. Why? Because exoskeleton just looks quite different from robot hand in the camera frame. And to solve this, we'll create a data processing pipeline to resolve this. And so you already have a joint encoder to record the hand motion, so we can simply replace same actions on a target robot hand. Then we run the SAM2 on the two videos to segment out the exoskeleton and robot hand from the video. Next, we use flow-based imprinting method to replace the exoskeleton pixels with the background pixels to get a very clean background. However, and we also need to compute the visible robot pixels. And to do that, we compute the intersection between the exoskeleton mask and the robot hand mask to preserve the natural occlusion between the hand and also the object. And finally, we can simply paste the visible part of the robot pixels over the background pixels to get the high fidelity robot hand video. Okay, so we evaluate our DexUMI systems over two different hands, one under actually the Inspire hand and the other is fully actually the X hand, on 5 different tasks. Those tasks require precise, context-rich, and long horizon manipulation skills. So we have fully open source our code and our CAD on our website, and also including very detailed tutorials. Yeah, please feel free to check out. And I think this is like one attempt trying to extend the idea, like collecting in the wild data, on the hand. And this is our version. We also have an excellent version from Haoshu's like DexUp and also the DexY from Tony's. Yeah, but we are excited about the overall directions to collect in the wild data. Thank you.
Okay, our next speaker will talk about DexUp.
Hello, everyone. I'm Haoshu.
Okay.
Yeah, I'll just switch. Okay. Hello, everyone. I'm Haoshu. Today, I would like to present you DexUp, Dexterous Exoperation for scalable robotic manipulation data collection. So nowadays, we could see many cool robot videos, right? We could see many cool humanoids. But one interesting thing is, like, if we look at their hands, what they are doing is basically like use a dexterous hand, reach an object, grasp it, and then move it to another place. In other words, it means that most robots are using their dexterous hand as a simple parallel jaw gripper just for pick and place. But why do we spend so much money and build such a hand, but just to do pick and place? What we really want is some like truly dexterous behavior. For example, we want robots to be able to use articulated tools, do a hand orientation, or like assemble small parts. And what makes them hard is that it's really hard to collect dexterous robotic manipulation data through teleoperation. So today I would like to introduce you DexUp, which is a hand exoskeleton that allows us to collect real-world dexterous manipulation data with direct feedback to humans. So basically, like we decouple the robotic hand and the wearable exoskeleton. In that way, we are able to put many different tactile sensors on the passive robot hand and feel the force to the robot hand by the linkage design. And on one hand, on another hand, we put position encoders at each joint so that we can capture the joint configuration of the robot hand. And for the tactile sensing, we actually embedded with a full hand tactile sensor. So this is an example. And such tactile sensors, they're all vision-based. And decoupling the passive hand from the human hand can give us very high freedom to choose many different tactile sensors. That's the same as a real robot hand. Okay. I don't think you logged into the account. Okay. Do you think you can log into the account?
I think probably not. This is not my computer.
Oh, I see. Okay. Well, okay. Then basically, we have actually many cool videos, but unfortunately, it's not logged into the account, so I cannot play them. but we have some real actual demo like in the robot demo. So please feel free to join our real robot demo. Thank you.
Okay, so our next speaker will, so let's welcome our next speaker.
Hi all, my name is Kailani. I'm at UC San Diego and I'm a first year PhD student. I'm excited to present a workshop paper. It's very much in progress of hardware optimization for in-hand rotation. So in like the recent in like the last 7 years, we've had a massive explosion of different types of control policies and really an advancement of control. So in 2018, you have like the Rubik's Cube optimization solver with using PPO. 2022, you get the in-hand manipulation rotation with fingertips using RMA. And since then, we've had an explosion of other techniques using dial MPC and other techniques, or even with tactile sensors such as like synesthesia. And these have sort of iteratively like bounced back and forth between really fine-tuning different like new control policies and having different types of hardware. So for example, in 2020, we get the Inspire hands, we get the Leap hand, and we just get an explosion of all different types of both anthropomorphic and super non-anthropomorphic robotic designs. And so we can look at both this and in nature and say, okay, like maybe the design space for manipulators is actually quite massive. For octopi, you can solve a Rubik's Cube, and for jellyfish, you can actually debone a fish, right? So these seems like things that are maybe like, the search space is maybe actually really quite large. And so one good question that we can try and investigate is how can we effectively explore and minimize this design, effectively explore this massive design and control space for dexterous multi-fingered manipulation. For example, this is like an Allegro hand, and there's a bunch of different parameters that we can try and optimize. There's damping, mass inertia, body scale, body length. And if we try and optimize all of these at once, and each parameter has such a wide space, when you do them together, it's quite a large search space. One thing we can do is we can use Bayesian optimization to try and figure out which parameters actually matter. So we can take, for example, friction, and we can say set a minimum and a maximum, do Bayesian optimization based off expected output using those values, and then run NPPI or another simple controller, and just keep iteratively doing this in order to figure out which parameters actually matter. Once we do this, we have a subset of parameters that actually, maybe are good parameters for doing more optimization. From this, I found that friction, geometry, shape, impedance, which is softness for your fingertips, and some other parameters quite matter. So once you have a much more refined search space, one thing you can do is you can do a joint search now, because it's still large, but it's a little bit more constrained. And so you can use, again, Bayesian optimization, do it all of these parameters, and hopefully get a better design. So you can take the Allegro hand, do rotation on your palm, and hopefully get some prediction or some information out of it. Here we find that objects matter, scale is helpful, and having like smaller medial scales. But this is a Allegro hand that's now optimized. And when you can, sort of taking across all these different parameters, we can find out that yes, geometry super matters. Having longer fingertips leads to better dexterity. Having slightly soft bodies helps a lot with controllability. Having a higher friction between this range of 0.7 to 0.8 always wins. And the control range super matters, but these hands are already very fully actuated, so it didn't really matter too much. But this is not the task that we trained on. This is actually a different task. The task I searched over was having a cube in the palm and rotating it on the palm. This is having a different object that we haven't seen before and with a different controller, right? Just showing that we can actually generalize from doing this search and not just hyper fixate to this smaller group. But yeah, and that's all. Okay, thank you.
We have seen the DexUMI presentation, and our next DexWrist.
I'm going to be presenting on DexWrist, a robotic wrist designed for constrained and dynamic manipulation. So current robotic wrists and arms in general are not equipped for constrained, dynamic, and real-world tasks. And a lot of this comes down to the fact that they have stiff actuation with harmonic drives. They have oftentimes coupled kinematics where multiple motors don't have one-to-one mappings to their degrees of freedom. And oftentimes they're also just non-anthropomorphic. They're huge, if anyone has used these arms before. And this just leads to difficulty in learning and unintuitive teleoperation, and eventually a slow data collection feed in these constrained tasks, or just being unable to do the task outright. So DexWrist solves all these issues, and it can be integrated onto most robotic arms and grippers given sufficient payload capacity. So the first place where we manifest these advantages is in this constrained task example here, where we have just a stock Agile X arm trying to reach out of the back of a very cluttered fridge. And yeah, it just can't fit. Its degrees of freedom can't contort correctly. But DexWrist, having much the kinematics like a human wrist, is able to reach behind and grab the can out of the fridge around all of these very cluttered objects. And this is in contrast to a lot of demos that you see robot arms do with fridges, where the fridges are very empty and they can very easily grab the object. And we found that in our testing that, at least with this example, we found a 4 times faster speed and policy rollout collected on the same number of demonstrations and training diffusion policy on both, and a 20% higher success rate as well. DexWrist is also capable of very dynamic tasks. So here we have a pre-scripted sequence to show a bottle flip, where this flip is entirely in the speed of the wrist. And we also find faster teleoperation, where we did 3 difficult tasks, difficult constrained space tasks. One, computer space, and that cluttered fridge example you saw earlier. And we found that DexWrist is able to complete much faster teleoperation in all of these examples. And so every piece of hardware always says that they can do some new thing, but the reasons why the DexWrist is actually able to achieve this is by addressing the major concerns we had earlier. First of which being stiff actuation. So a lot of these harmonic drives have very high gear reductions, which means they have a high reflected inertia, which means that they can't change direction quickly, they can't move very fast, and they lack torque transparency, which means that you cannot infer your torque from your input current. This is the fastest video of one of these arms I could find doing a task. And if you'll see the demo that I give later, you'll see that this is not fast. But yeah, the result is we can't have as dynamic motion, and that motion is not as compliant. Next, we have coupled kinematics. So in this example here, I show Unitary G1 ankle, and we see that each of those 2 black linkages, we need to control them in a very coordinated movement in tandem to move just 1 degree of freedom or the other. So to move the ankle up and down, which is a simple motion, you have to move both of them forward, and to move it side to side, you have to move them in opposite directions. And this complicates control greatly. And finally, DexWrist matches the kinematics of a human wrist, which allows it to fit in constrained spaces. And it solves these issues using dynamic actuation. I don't know why this is lagging. Okay, there we go. That is not sped up. Okay, yeah, now that's not sped up. Those decoupled kinematics where each motor controls 1 degree of freedom separately, and this anthropomorphic design that matches a human wrist. And if you'd like to learn more, check out the website, and we plan on distributing these, but also making it open source if you want to build one yourself, and check out the hardware demo later as well.
Our next speaker will be talking about AnySkin.
Hey everyone, I'm going to be talking about AnySkin, which is this magnetic tactile sensor that we've been working on for the past year. So starting off about like why we need tactile sensing. So there's a lot of tasks that as humans we do in our environment that require force sensing that like would be really hard to do without it. And as we start putting robots into environments where they interact with start interacting with humans, we want them to be force aware and perform sort of robust, dynamic, and safe manipulation. So so this is AnySkin. So you have a magnetometer circuit board that goes underneath the magnetic skin. It takes about 10 seconds to put together, and you have a sensor. It will continuous signal from the sensor. And so why AnySkin? So there's a lot of reasons I could talk about. You get conformal contact, flexible form factor, it's replaceable, you have shear sensing. low cost and thin, but since it's a 3-minute talk, I'm going to focus on just one aspect of this, which is the lack of repeatability that you have across instances with tactile sensors. Sensors that you see are which have this like you look at the backgrounds and like you change your sensor and the background looks completely different. You have the same problem with piezoresistive sensors, you have the same problem with existing magnetic sensors. And what ends up happening then is when if you collect a bunch of data and now you want to train a policy on that and deploy on a new sensor, you're resorting to these techniques like heuristic thresholding, some complex calibration procedure, retraining, or in the worst case, just recollecting all of your tactile data, which is not ideal. We want a tactile sensor that can sort of do allow us to do something like this. So here is a USB insertion policy that we trained. This is a visual tactile policy. And now my collaborator will come like swap the skin, move this, move the USB port around. And now this with the new skin zero shot that's never seen before in the data, it's still able to perform this insertion task. And our hope is that we will be able to do this. This will allow us to scale. The way we improve repeatability, just for some background, this is how magnetic sensing works. You have a magnetic elastomer that deforms on top. And below that, you have some magnetometers that are detecting this deformation as changes in magnetic field. And so we have, for fabrication, we mix elastomer, we add some magnetic particles and pour into a mold. And then we use this pulse magnetizer to magnetize these skins. And we get really strong, consistent signal that improves over past magnetic sensing skins, as well as other sensing skins. And we can print in whatever shape we want, depending on the mold that we make. And that really allows us to do more tasks like this, which are really precise and are able to generalize zero shot to like changes in the skin, which is something that will happen often if you use tactile sensors, because you want a soft surface that is going to rip and tear as you use it more and more. So I'm just going to skip through this. And so we are able to get cross-instance generalizability far more than any other tactile sensor that we've been able to test. And year or so, we have this is a bunch of people outside of like completely unrelated to us who've been able to use these skins. We have had 250 sample requests. We've shipped out about 70. And we also has been selling these now that you can buy samples from. But if you have, reach out and I'll get the poster session. Thank you.
Our next paper is eFlesh.
Hey everyone, I'm Venkatesh from NYU. I'll be talking about our new magnetic sensor, which was done sort of as a successor to AnySkin. And we sort of looked around and we asked why are touch sensors not everywhere in the community? And these were the answers we got. They were usually tough to fabricate or inconsistent or broke often. So now, very excited to present eFlesh, through which you can just 3D print your robot as a sensor. And the key principle here is that deformations on the surface produces changes in magnetic fields. So now how we get these is through two key components, which is a compostable deformable lattice, which is composed of these microstructures, and we put it together with magnets. And now to go on a little background, why microstructures? It can be fit to any shape. With a simple tuning, you can just choose your own mechanical properties. It's inherently easy to fabricate, and it can also be made compliant. So your workflow is going to look something like this. You start off with a design, you encompass it with a micro, and then you trim outside the initial shape. So a little more background on why Cut-Cell, what exactly are Cut-Cell microstructures. So we do this pre-computation given a target Young's modulus and sort of study how the cell deforms as you increase the deformation by how much you're deforming. And we stitch these cells together to sort of adhere to the initial Young's modulus specified, which essentially can be fit to any arbitrary shape. So now you, as a user, what you would essentially be doing is you choose your STL file and then pass it through our software. And then you basically get a sensor with pre-built pouches for magnets. And then you just send it to your 3D printer. And your active fabrication time is roughly 20 to 30 seconds, which just involves you inserting standard off-the-shelf magnets. And going back to the customizability, robotics in general, we have different applications. Say, if you want to put it on a quadruped foot, you would want it to be stiffer. But if you want to say pick up an egg, which I'll be playing in the next video, you would want it to be more sensitive and softer and have better capturing shear force and more sensitive in general. And what this allows you to do is you can also print large surface areas, and 3D printer is your only bottleneck in making sensors. And it retains the same repeatability as AnySkin, and we train the same visuotactile policies, and we're able to do some very precise tasks that involve reasoning low-level contact details, including shear force and very precise normal forces as well. I'll let this video play out. And as the community is very interested, the one question is interference and repeatability. As you might have seen, the repeatability, there's very little standard deviation. And for interference in magnetic sensing in general, we sort of swap the polarities, and now we maintain only a local field. And the alternating eFlesh, as you can see, is far lesser than what the actual signal corresponds to. Visit our website and come find me at the poster session for more.
Okay, our next speaker will be talking about AFab.
Good morning, everyone. I'm excited to introduce SAEF, our new generation foldable cross-embodiment teleoperation system designed for force awareness, dexterous control. Let's begin with a simple question. In teleoperation, vision is often used to close the loop through position, but are there any other feedback signals that we can use? So most current system often suffers from 3 major drawbacks. They are bulky and non-portable, the lack of proper force feedback, making precise manipulation difficult, and they are usually tied to like one specific robot, which restricts the generation. These issues make it hard to scale teleoperation or apply it across a diverse platform. That's why we introduced SAEF, which is foldable, portable interface, and sensorless for force feedback. And it's robots. It is robot agnostic. SAEF what type with a plug-in. So on the control side, we achieve full 6-DOF manipulation with a 3-DOF robot input arm, which you can show at the left. And we can use the wearable IMU glove or just IMU sensor with a gripper controller for the wrist orientation. With the bear, it's easily to switch between the gripper gloves, or even you can just control the arm. We compute the target and effector position and use this diversion from the actual position to render the sensorless force feedback, as you can see on the right. And those ACE data fit into the hybrid PD and the inverse dynamic controller, allowing precise and responsive control even without external sensors. So we test SAEF in the both simulation and the real hardware, and find it significantly improves the manipulation in contact-rich tasks like blind insertion, which is this, and because of the sensing and locating the holes and or the stacking the box by the order of the weights, quite complex like mechanical structure. So in short, SAEF enables a realistic, portable, and scalable teleoperation, paving the way for dynamic teleoperation and policy training. So we will be demoing our system at the back of the class. Feel free to stop and try it yourself. Thank you.
Thank you for attending our workshop, and all of our presenters will have their poster at the Family Plaza from 108 to 123, and we will also have some demo